Okay, so today we are going to move on to the third section in chapter 4. So far we've done exponential growth and exponential decay, and today we are going to introduce the number e, known as Euler's number. The number e as the base of an exponential function, and we're going to use it in some real life problems as well. So just a little bit about what this natural base e is. So the history of mathematics is marked by the discovery of special numbers such as counting numbers, zero, negative numbers, pi, and imaginary numbers. In this lesson, we are going to study one of the most famous numbers of modern time, and it is called the natural base e, and it is also known as the Euler number. And we use this variable e to denote that. So now there's actually a button on your calculator for this. So if you go onto your graphing calculator and you look on your keypad here, over here on, just clear that out for us. Over here, right above the divide sign in my calculator, it's in a blue, so yours may be a different color depending on what calculator you have, but I have that little E there. So if I wanted to get that to pop up on my screen at some point, you would just hit your second key, and then I'm going to hit my divide sign. I get that E to pop up. Now, very often we're going to use this E as a base, and we're going to be raising it to an exponent. So you could just type in the E and then use your little caret key and then do your exponent if you wanted, like E to the third power, for example. But there's also one that's already set up as a base and being all ready for you to raise it to something. And I believe that's over here on the left-hand side of your calculator where the button says LN. And that's something we'll get into next week. But if you go second and then the LN button, you'll see that E pop up already with an exponent ready for you to type in. So those are where those keys are found on your calculator. So as we go through the lesson, if you're kind of like, okay, where do I get this from? That's what you're going to do. Okay, so let's kind of talk about exactly what it is. So if you were to take this portion here, and this looks very familiar, it kind of reminds me of one of those summation formulas we did in chapter 7. But if you take 1 and you add 1 over n to it and then raise that to the nth power, what are you going to get? So let's start out with just n being a 10. And then we'll do it as a 10 squared, which is obviously 100, right? And then 10 cubed, which is 1,000. And just kind of see where it's going to go. So it's going to approach something. So if you remember when we talked about asymptotes and with exponential growth and decay and different things like that, or with the sums that we did in the last chapter, chapter 7, sometimes when we add things like in the series, they don't actually equal something, but they approach something. So we're going to see that kind of happening here too. So it's a little bit similar to what we did in chapter 7 with those series. So if we take a look at this, and I put this in on my calculator. So if I go to my calculator, I'm going to do parenthesis 1 plus, now I'm going to put my little fraction in its own parenthesis, 1 divided by 10. Close that parenthesis, then close the original. Whoops, I did an extra one by accident. And then you're going to raise that to the 10. And we're going to get 2.5937. So let's just carry it out, I guess, about 4 digits for now. So it was 2.5937. Okay, so now we're going to do the same thing again, but we're going to increase that n value exponentially just to kind of see what happens to the number. If we just went to 11 and 12, we wouldn't see very much change. So this time we're going to do 1 plus, and then 1 over 100, close both parentheses, and then we're going to raise it to 100. And now you can see it's 2.7048. 2.7048. So now this time we're going to use that n value as 10 to the third, or 1,000. So 1 plus 1 over 1,000, close both of your parentheses, raise it to 1,000. And now we have 2.7169. So interestingly, when we went from 10 to 100, we had a little bit of a jump, right? But then when we went from 100 to 1,000, which is a much bigger jump for the n value, the sum there actually was smaller. So now let's do it with the 10,000 to see what happens there. So 1 plus 1 over 10,000. And then we're going to raise that to 10,000. All right, now notice that saying that my calculator has an overflow here. I may have just typed something in wrong, let's say. Oh, I put an 11 in by accident. That shouldn't have happened. Okay, so 1 plus, parenthesis, 1 over 10,000, and then we're going to raise it to 10,000. And we get 2.7181. 2.7181. So now you can see it's kind of holding at 2.71 and just the other digits are going. So for the next two, you could put those in your calculator as well. But this is 2.71826, and I carried an extra digit just so you could see. And the next one will be 2.718280. So you can see it's kind of starting to maintain its value, and just the very last digits are changing. So we can say that it's approaching something. So what number is being approached as n gets larger? So the larger that n value, we are approaching this Euler's number, which is 2.7182, and then, whatever else after that. So it's right underneath there for you. So an important base often involved in exponential and logarithmic functions is the natural base e. It is an irrational number, so similar to pi, right? It's a decimal that continues on to infinity with there's no pattern to the numbers or anything like that. And it has this value here, 2.71828182, so forth. And obviously that would continue on because it's irrational. So essentially, as your n value, I should say as n approaches positive infinity, so as your n is increasing, this little sum here is going to approach e, or this 2.718 irrational number. So how does this help us, or where do we use it? Okay, so we're going to use it with some exponential functions, and we'll get into that on the next page. But first, let's talk about how we can use e or manipulate e mathematically. So when we use the e with these different expressions here, we're going to treat it just like you would treat any other variable as far as, multiplying and dividing and all those sorts of things. So if we look at these problems, we see that we have these e's in these little exponential expressions, and we want to simplify it. The same rules that we used back in chapter 2 that apply to like x's or y's or any other variable, we're going to also apply to the e. You're going to just treat it. Because remember, a variable represents any number, so whatever you can do with that variable, you can do with the e. So if we are multiplying two bases, as long as they're the same, we can add those exponents. So this would give us e to the 5th power. Another option for getting that is, remember, when you have a negative exponent, you can move it to the bottom. So another option for this problem would have been to move the e to the 4th to the bottom and make it positive, and then you would subtract those exponents, still getting e to the 5th. So again, same exponent rules that we did earlier in the year. Okay, number 2, we have a negative exponent, but it's outside the parentheses. So anything outside parentheses is going to get applied to everything inside. So this will be 5 to the negative 1, and then we will have e to the, and when we multiply those two exponents, we get positive 2x. Now, of course, we don't like negative exponents, so we would have to move that 5 to the bottom, and then 5 to the first is just 5. So that's what we would get for that one. Okay, moving on to number 3. First, I want to get rid of my parentheses. So this little exponent here is going to go to each of those terms. So I'm going to have 2 to the 3rd power times e to the 12th. So remember, when you have a power to a power, you multiply the exponents. Now, 2 to the 3rd is 8, and e to the 2nd times e to the 12th, I would add my exponents, and I would get e to the 14th. All right, and then finally, this one here, again, I like to get rid of my parentheses first. So now I have 1/3 to the -4th power times e to the, when I multiply those two negatives, I get a +8. Now my 1/3 has a negative exponent, so I'm going to, you could distribute the -4 to each number, or you can just flip the fraction. So I'm just going to flip it, so it becomes 3 to the 4th. And then, of course, 3 to the 4th works out to be 81. So it's 81 e to the 8th. And if you went a slightly different direction but got to the same place at the end, then that's totally fine. Okay, so moving on to the next page, evaluating the expression, and it says round to the thousandths place. So we're just going to be basically putting these in on the calculator just to make sure you're familiar with how to do that. So like I showed you before, if you're going to do e to the 3rd power, you've got two options. You can use the little e that's right above your divide sign and then use the caret to raise it to the 3rd power. Or you can use the second key and your ln, which already has it raised, and then you just have to put in the 3, and you're still going to get 20.0855, which would round to 0.086. So we have 20.086. Okay, next one, e is going to raise to the -0.12. So I'm going to use my key with the e as a base, and then I'm going to put in -0.12 as my exponent, and it's 0.8869, which would round up to 0.887. Okay, next one, e raised to the square root of 5. So again, I'm going to use my e as a base, and then I'm going to raise it to the square root of 5, and I get 9.356. And then finally, I'm going to do my e raised to the -2 over square root of 3. Now be careful on this one. You definitely want to put parentheses around that. And some of the calculators, the older ones, when you do a square root, it's going to put a parenthesis there. So you're going to have to close that as well. My calculator and the newer ones, you don't need to do that, but the older ones you will. So when you go to plug this in, you're going to do second ln to get your e, and it's raising it up already. So now I'm going to do in my parentheses -2 divided by the square root of, was it 3, right? Yeah, 3. Now, if you have one of the older calculators, you're going to need to put parentheses around the 3 and then close your parenthesis for that entire exponent. And you would get 0.315. So just make sure you're getting the right answer. If you're not, you probably missed a parenthesis or something. Okay, so now we're going to basically just kind of do the same stuff we did the last 2 days with the exponential growth and decay functions. These are going to graph very similarly to that. So a function of the form y equals a times e raised to the rx, it's very similar. So if you look at this, when we were doing growth and decay, we had a times b raised to the x. So the b value here is e to the r. And that's called a natural base exponential function. Again, just like we did with growth and decay, the a values have to be greater than 0 in reality to be these. Theoretically, yes, sometimes there's a negative, but realistically, that would be a positive. This time, the r value can be greater than 0. So that's just that little exponent. Before we've referred to this actual b value. So if you think about it, if you have a number greater than 0 as your exponent, whatever that e value is, the e value holds, right? It's 2.7 whatever. So when you take 2.7 dot, 18 blah blah blah, and you raise it to a number that's positive, that's going to be growth. So your b will be greater than 1 when that happens. But if you have a negative exponent and you take 2.718 whatever and raise it to a negative exponent, you're going to get a number that is smaller than 1 that will become a decay function. So if you look at this example up top, when we took the e in number 2 and we raised it to a negative, we ended up with a number less than 1, which would have made this decay. Okay, but if we took it number 1 and we took our e value and raised it to a number that was positive, this became a growth factor. Same thing over here. Square root of 5 is actually like 2 point something. So again, we're taking our Euler's number, we're raising it to a positive. So that would be a growth factor. And we can see that because it's 9.356. And then this one here, we were raising it to a negative. So that one would become a decay factor. So when you take your E and raise it to a power, if it's a positive power, it's going to be a growth factor. If it's a negative power, it'll be a decay factor. Okay, so let's see what that looks like in terms of a graph, right? So if I want to do a growth function here, and I'm just going to do my basic thing starting with 0, right? So if I raise E to 0, it's just going to become a 1, right? If I raise my E to a positive 1, it's going to be 2.7, whatever. If I raise my E to negative 1, what's going to happen then? So if I raise my E to a negative 1, I'm going to get 0.3678. So I'm just going to round it to 0.368. Now, of course, you can also do this on your graphing calculator as a y equals. So I can just simply type in my E, and I can raise it to x. And then when I go to my table of values, I can get the numbers from there. So negative 2 would be 0.135. And 2 is 7.389. 7.389. Now, in any event, we know that this is going to be growth here because it's the R is a positive, right? So if I were to graph this here, 0, 1, negative 1.38, negative 2.135, and then we have 1, 2.7, and then 2 would be 7.8. So I think it's like right here at the top. Now it's telling you here that the R value is 1. You might be like, wait, what do you mean it's 1? Well, because is there a number here in front of the X? You don't see anything there, then you know it's a 1. So in this case, the A is 1 and the R is also 1. Okay, so now we look at the next one here. Again, the A value is 1 because that would be right here. The R value this time is negative 1. So whenever the R value is a negative, we know this will be a decay factor. The E raised to the negative becomes a decay factor, so therefore it's going to be a decay function. So again, we can put this in on the calculator to get the points. That might be the easiest way since you've got this base of E. You're not going to be able to do that in your head. So I just go to my y equals. I'm going to type in my Euler's number, and I'm going to raise it to negative x and get my chart. And I have 7.39, 2.71, 1.37, and the last one was 0.14. I'm just going 2 places. All right, because all those decimals are going to be estimated when you plot them. So negative 2 and 1, 2, 3, 4, 5, 6, 7.39. Negative 1 and 2.71. 0, 1, 1.37, and then 2.14. And we can see that it looks like a decay function. Okay, so again, let's talk about domain, range, and asymptote for these. So for the first one here, our domain, we know for all these functions is all real numbers. It's not going to change here either. The range is the y values. Well, the entire graph is above that x-axis, so all the y's have to be greater than 0. And the asymptote, just like before, is y equals 0. So you don't see a k value adding to the end like we did with the growth and decay. We know that that's 0. The same thing's going to occur on this decay function. So our domain is all real numbers. Our range is still y is greater than 0, and the asymptote is y is equal to 0. So those domain, range, and asymptote rules are still going to be the same that we did with the exponential growth and decay. Okay, so tell whether the function is an example of exponential growth or decay. So again, as far as the a value is concerned, just like we did in the last two lessons, that a must be positive technically for it to be any sort of exponential growth or decay, because you got to start with something, right? All of these have a values that are positive, so you don't have to worry about any neithers, popping in here. So now we're really just focusing on that b value, which is that b value in this case is the e to the r. Okay, so if that e raised to r is a positive, and you'll know that because it's a positive exponent, or it's greater than 1, the b value, then you know it's going to be growth. If that r value is negative, then your b will be between 0 and 1, it will be decay. So that's really all you need to look at. So I'm just going to put that in parentheses. So this one here, you have an e raised to a negative, so this will become a decay factor and therefore be a decay function. For this one here, you have e raised to the second power, which is going to become a growth factor since the r is greater than 1, or positive, so it'll be growth factor and a growth function. This one here, 0.5 is still positive, so when you do e raised to 0.5, you will have a growth factor, so it'll still be growth. Here, you have e to the negative 8, so that will be a decay function. Here you have e raised to the negative 0.25, so that will also be a decay function. And here you have e raised to the positive 9, so that will be a growth function. So pretty straightforward. When you have the e, you just have to look at the exponent, is it positive or negative. Okay, so we're just going to practice some graphing with the e's. Okay, so the natural base e logarithmic functions. And the graphing is very similar to what we did prior. You can still do that shifting with the h and the k. So on the bottom 3, we'll see that. But the first 3, we don't have any h's and k's here, so we don't even have to get into that just yet. But it's pretty much the same thing we already did. You're just going to want to use your calculator a little bit more. Okay, so if we're going to do our table of values here, I always just like to put in these basic 5 numbers. Now, of course, when I raise anything here to 0, when I make my x 0, the r and the 0 turn to 0. Anything raised to 0 is 1, so I know that that's going to be 2. So just like it was for growth and decay, if you don't have an h and a k in there, and you put in a 0 for your x, your y value is going to be that a value, which in this case is 2. And then after you do that, you're probably just going to want to maybe plug in 1 or 2 more from your table. So down here, I'm going to do my y-intercept, which is 0, 2. We just talked about domain. It's still all real numbers. The range and the asymptote in both of these cases, it's y equals 0, and then y is greater than 0. Now, one other thing, as I was looking through some different things, I write this r for all real numbers, but another way that you may see it written if you come across it, like when you're Googling stuff or even on the quizzes, I've seen it written like this. If you see something where it says, x is in between negative infinity and positive infinity, like that, that's also another way to write all real numbers. So if you see that, I changed it on last night's, but if you see that on tonight's quizzes, that just means all real numbers. So I just want to point that out. Okay, so I'm going to be using my calculator a little bit more for this lesson because I cannot do Euler's number in my head. So 2 times e raised to the 0.75x, and then I'm going to go to my table. I already know that it's going to graph a growth function. So I have 0.45 and 0.94. 0.45 and 0.94. I'm just going to go 2 digits because we're estimating these points anyway. And then for 1 and 2, it's 4.2, and then I'm just going to make that 8.96. 4.2 8.96. So when I go to graph these, -2 and 0.45, you could probably make these tenths if you wanted to. Then this one here, 0, 2, 1 and 4.2, and then 2 and 1, 2, 3, 4, 5, 6, 7, 8, and just about to the 9. There is our exponential growth function. Okay, so taking a look at number 2, before we do it, let's say, is it going to be growth or decay? Well, because my r there, my exponent for my Euler's number is a negative, we know this is going to be a decay function. Okay, I also know that if I put in a 0 here, my y-intercept is going to be 0 and 1.5. My domain is all real numbers. My asymptote is y equals 0, and my range will be y is greater than 0. So now I just need to get some more points. So I have 0 and 1.5, but I might want a couple more to graph on there to get my graph. Okay, so when I type this one into my calculator, go to my y equals, I'm going to do 1.5 times e raised to -0.5x. Go to my table. Oops, I must have typed something in wrong. Let's see here. All right, 1.5 times e raised to the, oh yeah, that's what happened. Okay, let's try this again. 1.5 times e raised to -0.5x. There we go. Now I'm going to go to my chart. So I'm going to just do 4, 2.5, and then 0.9 and 0.6. 4, 2.5, 2.9, and 6. Hopefully I got that right. Or 0.9, I don't know where it is. 0.9. Okay, and then that one, last one was 0.6. Okay, 0.6. All right, so -2 and -4. Or wait, hold on a minute. That's not right. -2 and +4. Okay. -2 and 1, 2, 3, 4. -1 and 2.5. Then we had 0 and 1.5, 1 and 0.9, and then 2 and 0.6. So, whoa, that was really crooked, but you got the idea. That's my exponential decay function. Okay, and then the third one, without an h and a k, we have -3 being raised to e to the 0.5. So now, without this negative value for a, I would say that this is going to be a growth function because my exponent is positive. So you would say, okay, it's going to go like this, right? But because of this negative a value, it's actually going to reflect over that x-axis. So it's going to look like that. So it's actually neither exponential growth or decay. So in this case, as far as, because my h and k are not there, my y-intercept is still going to be 0, -3. My domain will still be all real numbers. My asymptote will still be y equals 0, but this time the range will be y is less than 0 because it's going to reflect over that x-axis. So now getting the points, I already had the 0 and -3. But if I want to get a couple more points, I'm just going to use my calculator. And I'm going to put in -3 e raised to 0.5x. Go to my table. And I have -1.1, -1.8. So -1.1, -1.8. And then I have -4.9 and -8. I think it's actually 8.2, but all right, so then I'm just plotting these -2 and -1.1, -2 and -1.8, 0, -3, then 1 and -1, 2, 3, 4.9. And then 2 would be somewhere down here. So we're going to kind of, and as you can see, it is reflected over that x-axis. Okay, so moving down to the bottom, we want to take a look here and identify those H's and K's. Okay, so again, you could use that graphing the parent function like we were doing in the growth and decay sections and then shifting it according to H and K. But because you're probably going to use a calculator anyway, I'm not going to worry about doing the parent function and the other one as long as you understand how it was shifted from the parent function. So right here, we know that the A value is 4/3. The H, just like before, is always the opposite sign. So it's whatever's being subtracted from X. So right here, we can see we're subtracting a +3, and my K value is +1. Now, because this is a little tricky because you're like, okay, well, what's my R value here? The R value is technically a 1, sort of like a 1 times that X minus 3. So this can be a little bit tricky. So we do know that this is going to be growth. We're not raising anything to a negative. So when we go down here to the bottom, because of the H and the K, just like we did with exponential growth and decay, we're going to shift 3 to the right because H goes left and right and 1 up. So that's not going to change. 3 right, 1 up from the parent function. The domain is still going to be all real numbers. The asymptote will be y equals that K value, which is 1 in this case. And since our A value of 4/3 is positive, our range will be y is greater than 1. The y-intercept, however, will be 0, and then whatever you get when you plug in 0. So we'll use the calculator for that part. So now when you go to the calculator, it can be a little tricky because there's a lot going on with these. So we have 4/3. So I'm going to put that in parentheses right there. Then we have the E raised to, and I'm going to put parentheses here, X minus 3. Close those parentheses, come back down, plus 1. So now I'm going to go to my table. I can see 0 and 1.0664. So I'm just going to make it 1.07, wherever that is here. 1.07. And if I'm doing my little chart here, 0, 1.07, -2, -1, 1, and 2. Okay, so then my other numbers were 1.01, 1.02, 1.01, 1.02, and then 1.18 and 1.49. 1.18 and 1.49. Now you'll notice nothing went lower than 1, and that makes sense because our asymptote is y equals 1. So when I go to plot these, -2 and 1.10, 1.01, then we got 1.02, then 1.07, then it goes 1.18, then 1.49. So it's very hard to even estimate those, but it would kind of go like that. Let me see if I can get a couple more on there to make it a little more accurate. So 3 is 2.3, and then we have 4.6. So 3 is 2.3, and then here we got 1, 2, 3, 4.6. So I can make that a little bit more accurate. So if you have the room and the numbers fit, you can kind of see it going like that. And then even 5, if I want to throw 5 in there, it's 10. So then that's off the graph, but you get the idea. All right, so let's go down to the next one here. Okay. So looking at this problem here, my A is +4, so it could be growth or decay. But my R value is a negative, which means that this will be a decay factor. So we know this is going to be a decay problem. And my H right now, there is nothing adding or subtracting for the H. The H is 0, and the K value is -2. So to do my shifting, I would not shift left or right, but I would shift 2 down. My domain is all real numbers. My asymptote is y equals -2, and my range will be y is greater than -2. And the intercept we will get off our chart. It's going to be 0, 2, though. I'm just going to fill that in. Okay, so when we go to do our chart, our XY table, -2, -1, 0, 1, and 2. So again, plugging this in, we have 4 times e raised to -3x. Now, the people with the older calculators probably need to put parentheses around that, -2. And your table should look something like this. So we have, wow, 1,611. I'm not going to bother fitting either of those, so I'm just going to focus on these lower numbers here. So 1 and -1.8. And then 2 and -1.99, but really we're looking at 2 from that point on. So 0, 2, 1 and -1.8. So here maybe, and then after that it's pretty much going to 2's. So this is a very steep decay function. All right, and then let's do the last one. You're probably all graphed out by now. Now this one's a little interesting because you have this x plus 3. So we want to identify these different things. So in order to identify the r and the h, you're saying, okay, like what are these different numbers here? So we know that the a is the 1/2. And then this here is a -2. So that's my r value. So we know this is going to be a decay function. Okay, but in order to find the h, you actually are going to have to change this to -2x minus 6. So then we know that h is 6 and the k is -5. So if the h is 6, we're going 6 to the right. If the k is -5, we're going 5 down. Domain is always all real numbers. Our asymptote is y equals that k value, which is -5. Our range is going to be y is greater than -5 since the a value is positive. And then our intercept will be what we get when we plug in 0. And I believe it's approximately -5. And the reason I would do the squiggle is because I think it's actually like -4.9999 or something like that. Let's see. Okay, so again, putting this into our calculator. I'm actually going to wait before I put my grid. So we're doing 1/2 times the e raised to -2 minus 6. Bring in, oops, I've missed an x. Shoot. 2x minus 6. Okay, there we go. And then the -5 at the end. And then we go to our table. So you see how it's kind of leveling out at that -5 there. So it's actually -4.5, 0, -4.5. Everything else is kind of going to be down here. And then we go back to the negative. Oh, wait a second. Hold on. I might have typed this in wrong. All right, let's try it the other way. I might have done something wrong there. Okay, we're putting in our e, and then we're going to do -2 for the r, so x plus 3. So just put it in as it is. I was distributing it out, but then that was messing it up. Okay, so now here's what our graph is going to look like. Here is the table. So you got the -4.99 for 0, and then you'll see that it's really maybe -4 and -1.3 where it kind of changes. So right there. So it's going to kind of come around like that. All right. Okay, so hopefully you got the idea with the graphing, with the growth and decay. It's very similar with this E value as far as identifying all the different parts of the graph. Okay, and then finally, the last formula we're going to do, and you'll notice this little portion in here, the 1 plus R over N. Remember, that kind of looks like that compound interest formula that we did the other day. It is actually. But in the beginning of our notes today, we talked about that when the R value is 1, and we did 1 over the N, and we changed all the N's like 10, 100, and we saw what was happening, right? So when something is continuous, if interest were to be applied continuously, not like every X amount of days, this whole piece here would approach E, right? So that's why they replaced all that with this E. So whenever you see the word continuously compounding, instead of doing this whole long formula and putting in infinities in there, we would just use this Euler's number instead. So really, when you're doing these problems, you just have to look for certain keywords. So obviously, when things are decreasing, that's the decay formula, and we'll review this on Monday. If you see the word continuous, that's when you're using that E formula. And then, of course, if it's increasing, it depends on if it's being compounded at a specific time period or just generally. So if we deposit this $1,500, that's our principal amount in an account that pays 7.5% interest. We're going to use 0.075 for that decimal. And we're compounding it continuously, which tells us we're using this formula here. Now, the years is the T. Now, you have two options with this. You could just simply put in 1,500 times E raised to 0.075, and then you could just multiply that to, let's say, 1 or 3 or 8. Or if you keep it a variable, you can just put this in on your graphing calculator and get all three answers at once. So since we've been mostly using the graphing calculator, I would recommend you just do it that way if you're finding it for multiple years. So if you go into your y equals, you would type this in. So you're going to have 1,500 times your E, and then you're going to raise that to 0.075, and then your variable X or T. Then you go to your table, and you can find it for 3 years is right here, or 1 year, 16, 16, 80, right? So 16, 16, 80 would be the 1 year. That's how much money you would have after 1 year. After 3 years, you're just going to go down and look for the 3, 1878.50. And then after 8 years, 2733.20. Okay, and that's how you would do that. And you could do them individually, but on the calculator, it just gets all the answers in the one table. Okay, so let's go to the next problem. You deposit $2,500 in an account that pays 6% interest. You're going to use this as that initial amount and then 0.06 as your R value. Calculate after 3 years when the interest is compounded at these different times. So because it doesn't say continuously for the first two, we have to use that longer formula up at the top of your page. But for continuously, we will use the one with the E value. So for semi-annually, if you're looking at the formula at the top of the page, you have the P times 1 plus R over N raised to the NT, right? And we've done this one the other day. So I'm going to put in my $2,500 for my initial investment. My rate is 0.06, and because I'm figuring this out semi-annually, my N is 2. That's twice a year. And then it said for 3 years, so my T is 3, so 2 times 3 on the outside. So now when you go to put this in the calculator, you want to do those parentheses first, right? So you're going to do, in your parentheses, you're going to do 1 plus, and then you would do the 0.06 divided by that 2. And then you're going to raise that to 2 times 3, which you can probably just do that in your head and get 6. So after you get that portion, you're going to multiply it to that principal amount out front, which is the 2,500. and you get 2985.13. So 2985.13. Okay, so now let's do this for monthly. So if I'm doing this monthly, that means my n value is 12 because there's 12 months in a year. So I'm going to do 2,500. That's still the same. 1 plus 0.06. My rate is still the same, but now I'm going to have that over 12 because there's 12 months in a year. And over here, I'm going to do 12 times 3 for, so that means that over the 3-year period of time, this interest will be applied 12 times each year, which is 36. So now on your calculator, you're going to do 2,500 times whatever you get in here. And you're going to raise that to 36. So on my calculator, I'm going to do 1 plus parenthesis 0.06 divided by 12. That's my parentheses. Then I'm going to raise that to the 36. And then I'm going to multiply that to my initial investment of 2,500. And I get 2,991.70 cents. So 2,991.70 cents. And then finally, my third one is continuous. So this is where I'm going to use the other formula with the E, right? So my principal is still 2,500, but this time I'm going to do E raised to 0.06 times 3. So when you go to your calculator, kind of do it all in one shot. So 2,500 times E raised. Now, if your calculator raises, you don't even need parentheses, but if it doesn't, put the parentheses, and then you're going to need 0.06 times 3 for the 3 years, and you end up with 2993.04. So 2993.04. So as you can see, the more frequently that interest is applied, and continuous would be the most frequent possible, you would earn the most money back. Okay, and then finally, the last question. The air pressure at sea level is about 14.7 pounds per inches squared. As the altitude increases, the air pressure decreases. The relationship between P and K is P equals 14.7 times E raised to the negative 0.00004 H. Mount Everest rises to 29,228 feet above sea level. What would be the air pressure? So we're simply just going to plug this number in for H. So to find the pressure, 14.7 times E raised to negative 0.0004 times 29,028. And you'll just do that on your calculator. And you should get 4.6 pounds per inches squared. And I'll let you do that calculation on your own. Okay, and so that's it. Thanks for joining me. These are the 3 lessons, the first 3 lessons of chapter 4. So Monday we will review. I will put up a review for this, and then Tuesday we will have a quiz on these 3 sections. So please reach out, ask any questions if you have any, and that's about it. Have a great weekend.